At school, the curriculum only calls for us to study rectilinear motion. In other words, we only have to do calculation of motion in a straight line. Now, that doesn't mean that we don't need to have a basic understanding of the fact that velocity changes if there's a change in direction, or if we have an example where we're going around a circular track and we understand that velocity and speed are not the same thing. But we're not going to have to do calculations of velocity and acceleration if there's going to be changes in the direction. So we're going to keep it in a straight line. Acceleration is defined as the rate of change of velocity. Velocity is a vector quantity, so there's a direction, which means that acceleration is a vector quantity with a direction. Rate of change, again, tells me I need to divide by time. So I take the change in velocity, remember we symbolize change in with a triangle, over the change in time, change in time. The way that I work out the change in velocity is I take the final velocity, which is symbolized with a V, minus the initial velocity, which I symbolize with a U. This is going to come up quite a lot more later, so be aware of it. Final minus initial. If I take velocity as meters per second, and I divide it by seconds, time, if I were to bring that second to the top, I would have meters, seconds to the minus 1, seconds to the minus 1. So the unit for acceleration is meters per second squared. So it's to the minus 2. Be very aware of these units. Meters to the per second squared for acceleration, while it's just meters per second for velocity. As I said, acceleration is a vector quantity, and it results, if, for example, that car in the last example was going around the track at a constant speed, it would still have been accelerating, because there would have been a change in the velocity, and any change in velocity results in acceleration. You wouldn't have to calculate it though. When something is going at a uniform velocity, that means there is no acceleration at all, and we call that a state of equilibrium. In other words, all the forces are balanced when we've got no acceleration. If an object is increasing its speed, we normally say that the acceleration is positive, and when it's slowing down, we say that the acceleration is negative. Another word that we can use is deceleration, but in science we generally talk about positive acceleration or negative acceleration. The sign can also mean it's going in the opposite direction. So deceleration is really acceleration in the opposite direction. So when something slows down, it's almost like it is speeding up, but in the opposite direction. So let's take a look at this example. We've got a car traveling at 20 meters per second. The brakes are applied for 4 seconds, and the car uniformly slows down to 8 meters per second. What is the acceleration? Well, acceleration is final velocity minus initial velocity divided by time. At the end, it was 8. At the beginning, it was 20. So it's 8 minus 20. Final means end. Initial means start. And the time it took to do that was 4 seconds. So I land up with negative 3 meters per second squared. In other words, it slowed down at 3 meters per second squared. We can always calculate an instantaneous acceleration at very small velocity changes over very short periods of time. Then there's something called relative velocity, which we've sort of done when we did vectors. In other words, we can always measure relative to something else. We tend to measure relative to the Earth's surface, but as you're sitting where you are right now, if you were in space relative to the sun, you would be traveling on the Earth at 100,000 kilometers per hour. So that is always measured relative to something else. Remember that if you are walking on a train, there is a difference between your walking on the train relative to the ground or relative to the train's the train carriage. So let's say I'm walking backwards in this train at 3 meters per second, but the train is moving forwards at 10 meters per second. Relative to the train, I'm moving at 3 meters per second, but relative to the ground, I'm moving at 7 meters per second in the forward direction. If two cars are moving in opposite directions, their velocities relative to one another is faster than their velocities relative to the ground. So, and we've done examples like this, and they've come up in your exam and your tests and all of that. So let us say I have one car, and it is going at 60 kilometers per hour, and I have another car, and it is traveling towards there at 70 kilometers per hour. Relative to the ground, is traveling at 70 kilometers per hour. Relative to the ground, he's traveling at 60 kilometers per hour. But relative to each other, they are approaching each other at a speed that is those two combined. They will experience both their own forward velocity as well as the forward velocity of the other vehicle. So they are relative. The bug car is traveling at 130 kilometers per hour relative to the box car over there. And if they were going in opposite directions, let's say this vehicle was traveling in that direction, you would find that it would be moving away from this little bug car at 10 kilometers per hour.